All right. I think we are the time with our meeting. So I see some of our advisors also joined, Dr. Sheep, Dr. Murphy, and Paulo. I don't know if I'm missing anyone here. So thank you all for joining our first virtual event organized by Clarkson University ECS Student Chapter. And my name is Faride Hosseini Narui. If you don't know me already, I'm the president of CU ECS. And I'm so happy, like, in this the bright side of this pandemic, so it's give us opportunity so to have people and get to know people from outside of the Clarkson or peers in Montreal and Waterloo University ECS chapters. I welcome all of you and thank you for coming and joining and initiating this collaborative event. And I would like to thank Dr. Ajit Khosla for giving us such a value and accepting our invitation, for giving us such a great topic that he's working. I will give his introduction to himself because he will be doing much better job than me. I so at the end of the session, there will be a question and answer, but Dr. Khosla said he's okay if you can, if you, during the presentation, if you have any question, you can just interrupt him and ask your question. So the session will be in this way. And we will be posting the recorded presentation to our YouTube channel for those who's gonna miss the meeting. And yeah, that's it. I think I said what I needed to say, and I give the session to Dr. Khosla, and thank you again for joining us.
Okay. So I would like to thank all of you for inviting me to this online session of your student chapter. So I would start to share my screen. Can you see?
Yes.
You can? Okay, you guys can see it?
Yes.
So, okay. So, what I'm going to talk about is something which is going to be a little bit unusual from what you guys are used to. It was unusual to me as well when I started to enter into this area. You can interrupt me wherever you want within the presentation. What I would like to do in this talk is I would like to be as interactive as much as I can, and also a lot of emphasis is going to be on actually sustainability, which is not a new concept. It has been there for a long time, but sustainability is something which is becoming quite important right now. And to make a case for sustainability, I would talk about some data and like what is going around in the world right now. So by the way, I work at Yamagata University in Japan. So it's 10 p.m. for me right now, and 9 a.m. for you guys. So I'm 13 hours actually ahead of you. So the outline of my presentation is, I would just briefly, for those who don't know me, I would talk about my introduction, my education, work experience, what kind of education programs I develop and I try to push for them. And then I would talk about my research program. Then I would talk about additive manufacturing and sustainability. What are going to be the benefits of sustainability? Then I will talk about various challenges involved. what we do to overcome those challenges, and then I'm going to talk about some sensors, and also redox flow batteries. Um, and then briefly might touch on future work if time permits. And if you guys are interested, then I would push on towards soft robotics. I have eliminated soft robotics right now because I think we will not be able to cover all of that. Uh, um, hmm. so, so where am I located? Here is Tokyo. If you guys can see, I don't know if you can see my cursor or not, but like Tokyo, 2 hours, 2 hours north of Tokyo is a city, is a small. It's not small. It has a population of 90,000, and it's called as Yonizawa. Yoni means rice, not really rice, paddy field, and Zava means a small river. So it's a rice, no, paddy field, small river. So the name of the city when you translate it into English. Mm, so it's approximately 2 hours away, uh, 2 hours and 7 minutes from Tokyo by Shinkansen, which is a bullet train. So like we have roughly around so keep in mind that only faculty of engineering is actually located in Unizawa, and in Yamagata city, the rest of the faculties are located. Okay. uh, which is approximately 30 minutes, not 30, approximately 45 minutes to 1 hour by road. What is Unizawa famous for? We have really expensive, really nice, actually, cherries which grow. We are famous for skiing. Japan's most expensive cherries, pears, and grapes come from actually Unizawa. On a professor's salary, obviously we cannot afford them. They're really expensive, probably um, one pound would cost you $100. So it's that level expensive, especially your uh, especially your cherries. Uh, hmm, hmm, uh, and you could see kind of an aerial overview. Oh, it's not really big city, but it's like 85 to 90,000 people live. But it is quite industrialized. Um, we have approximately a 500-old sake brewing factory, which is, even from my home, it is like 5 minutes walk actually. It's not that far. Um, mm, mm, and for folks who like to drink, probably sake is one of a really nice rice-based drink. If you come to Unizawa, it is known for its sake. We guys would go out for drinks. And probably our student chapter one is actually very active, which I had started here, and they won the outstanding student chapter for 2020. So the results are going to be officially announced in next few days. This was, I came to know because of board of directors meeting at ECS, which this is supposed to be confidential, but anyways, it's okay to mention. Yeah, so we have like approximately 200 professors just in faculty of engineering. There are approximately 50 companies. And on the next slide, I would try to show what kind of companies are there. Some of them you might have heard, you might have heard about them. Um, so so the kind of industrial network which you guys have it all began long time ago, which was in 1884. So most of you would know what actually saffron is, especially guys from Iran, Pakistan, India. You guys might be very familiar with saffron because it's used in like food. Um, hmm, so in Japan, what they used to do, there was a factory what was started called as Nita Dye Studio. They used to do dyeing of silk fabric using saffron. And so a lot of silk was exported from this small city. From after that, uh, when the first technical school started in like 1900s, in 1915, which started in Yonizawa. Uh, um, there was a spin-off company which is now known as Taijin. Um, in 1915, the first artificial silk was made, which in US we call as rayon. So the rayon fabric was discovered in actually Yonizawa at the school where I work right now. Um, and then there was a spin-off company which is now known as Teijin. Most of you would have a Teijin product in your home, one way or the other. If you have things like anti-slip laces, if you own a car, there would be one or the other product or a material which was designed or which was synthesized by Teijin, which is being used. Hmm, a very simple example is any kind of a anti-slip shoelace which you buy, or any kind of heat reflective film which you would buy. They are most likely to be coming from Teijin. A lot of automotive body parts, high density polymers also they make. Hmm. The other biggest achievement from the industrial hub, what we have is actually NEC, which is which makes your PCs, and the first notebook PC was built in 1984 in actually Unizawa City by NEC. Apart from that, recently we've had a big advancement of organic electronics. If you go to the Future Science Museum in Tokyo, there's a big globe which is shown on the right hand side of the screen. That is all made out of organic OLEDs. Mm, um, and we guys are pretty much known for white light OLED. The other famous company, which is an audio company called as Pioneer, are usually car audio systems were and still are made by Pioneer. That's also located in Yonizawa. And very close to Yonizawa is also your Geol, which makes your scanning electron microscopes, XPS, and so on. So there's quite a lot of industry, and there are small industries which actually support bigger industries. We work very closely with universities. A lot of funding for my research work comes from universities usually. Comes from industry. So industry invests a lot into development of like various technologies. Mm, mm. So moving on from here, we have a big center which we call as hospital for batteries. You name a battery, we have it. We have a full assembly line in which you could actually manufacture a battery. We do a lot of cycling tests, thermal testing, And it's like from A to Z, right from a coin cell battery to like lithium ion batteries, the whole of it, right from people who are working on electrode materials, right from electrode materials, and from A to Z, anything to do with batteries, you can actually do it there. Now a little bit about me. Since 2015, I speak like English, a little bit of Japanese, of course Hindi, which is my native tongue. I speak some basic Russian, Spanish. Of course, people who are anybody, if he's from Pakistan, I speak very fluent Urdu. I can read and write in Urdu, so it's quite uh, speak multiple languages. Um, mm, since 2015, I've been working in I've been working in Department of Mechanical Systems Engineering. Plus, I'm a visiting professor at San Diego State University. I have an adjunct professorship at Simon Fraser, and I'm a visiting scientist at NASA Ames. I was supposed to go for work. I'd taken time off from my university to go to NASA Ames for 1 year or more. But this COVID-19 happened, and I'm stuck. Mm, so we were planning to do some work along with some industries at NASA for in-space manufacturing. If you want to know anything about in-space manufacturing, feel free to ask me anytime. It's like who I am, from where did I do my PhD. So I did my PhD from Simon Fraser University. I did my master's in nanotechnology and microfabrication from University of Wales in Britain, and I did my bachelor's in electronics from University of Jammu back in India. What do I do most of my research on? It's like flexible sensors and electronics. I personally do not like organic electronics, although I have published quite a few papers in that area, but I do not like them. So I'm more towards silicon-based electronics, because maybe I have a bias also because my background is in that. Over the last 3-4 years, I've been heavily involved in 2D, 3D, and 4D printing. I'm moving away from conventional lithography and so on, or E-beam lithography, or FIB, and all those areas in which I used to work in. So 2D, 3D, and 4D printing, do a bit of energy storage devices, and like sustainability is now becoming a really big part, and especially I have embraced it since I've come to Japan, because that is what they're always geared towards. We did a pretty huge conference on 4D materials and systems in 2018, along with Electrochemical Society in actually Yonizawa, which had around 350 attendees from all over the world. Other leadership roles which I'm involved into: I'm editor for Journal of Electrochemical Society, Journal Solid State Science and Technology, Microsystem Technology, IEEE Nanobiotechnology, MDPI, of course, and right now I'm chair of sensor division. I will be stepping down next year in May, when IMCS would be conducted in May. IMCS ECS meeting in May, I would have stepped down as chair by then. And also I'm conference chair for 4D materials and systems. So these are the activities what I'm involved into. Anybody has any questions? Anything they want to know? Yes. Just go ahead.
Sure. Yes, Professor, are you in Japan right now?
Yes, I'm in Japan right now.
Oh, nice. Okay.
Okay.
That's great.
Maybe I should remove the background. I'm not in Hawaii. or yeah. Any more questions? Anybody wants to know anything, or should I move ahead?
I had a question.
Yeah, go ahead.
How has your transition from electronics to nanotechnology been?
How has my transition
From electronics in your undergraduate education to nanotechnology in your graduate education?
Mhm. How has my transition been? Okay, this is interesting. I mm, Hold of my bachelor's. Mm, I we had we, I had never done fab. I never did fabrication of devices. It was taking discrete components, making different circuits, even C++ languages, microprocessors, right from 8080 to 8085. We guys did all that stuff, studied all that stuff. But it had always fascinated me. How do these things internally? How do they make them? How do they work? So the basic theory we knew, like, there's a process called this photolithography, blah blah. But we had never we had never performed it because there were never facilities like that. Mm, um, mm, and um, it is also a difference in the education systems. So my transition from my bachelor's to my master's in nanotechnology, um, um, oh, it was quite easy because mm, there is a difference in the way in the education system. Uh, uh, when I moved to do my masters, um, we had a lot of hands-on labs as well, like going to clean room, fabricating, um, mm, um, using femtosecond lasers, atomic force microscopes. It was more exciting. Um, uh, and I had never been good at chemistry. I was always a user of chemistry. My knowledge in chemistry is as far as um, uh, extends to a point, and that how I can use it. Okay, I do not synthesize. I do not. I never carried out like synthesis of complex molecules or like whatever. Um, so that was quite alien to me. It's the transition. Your good transition also has to do with the professor under whom you actually do your masters. I was lucky enough to have Professor Ron Pethig. Professor Ron Pethig, he is known as father of dielectrophoresis. Dielectrophoresis is mm, motion of particles by virtue of dielectric properties in homogeneous electric fields. So he was a father of microdielectrophoresis, and I worked with him to develop lab on a chip, okay, devices. And plus, I got heavily trained into micro and nano fab uh, at University of Wales. So there was a lot of learning. The fundamentals were there, but there was a lot of learning, a lot of hands-on work as well. And also there's more emphasis on trying to understand rather than just problem solving. Okay, because there's this difference in education system. In India, we have to solve a problem. Okay, so we never went deep inside a problem to actually analyze it, think. Yeah, even simple things like vector analysis, as I could never imagine a vector field ever in my life, because that's not how the education was done. But I could solve any vector-oriented problem. I could do triple integrals, but I never knew what it really meant, right? But in my masters, I knew how to solve but I learned all that gap of what a triple integral could mean, or oh, like this is how you really make a device. That is how it is actually working. This is how you test. You read about a scanning electron microscope in a book versus when you go and do when you go and use it yourself. It's like entirely different. So transition was good. There was a lot to learn, but of course it has to do a lot with your professor as well. So if you want to move ahead and do a master's, you should work with a professor with whom it's always fun. The moment it starts to get boring for you, quit, leave it, because you're not going to do it in the end. So that's my advice.
Thank you.
Yeah. Anything else, or should I move on? Move on. Okay. So over last 10 years, just to tell you, it takes hard work. It's not something which would come up in a day. So what I have tried to do is to engage and work with a lot of universities, to actually set up collaborations. Right from Japan, right to Taiwan, to India, to Denmark, to Germany, Ireland, Britain, US, and also in Canada. So I quite a lot work with John Hopkins, Larry Nagahara, NASA Ames. We started this. We are working on some projects. Denmark Technological University with Anya Bozin. We've published a few papers on drug delivery and additively manufactured reservoirs for drug delivery. So like things like that, interesting stuff. So it takes hard work to build up this network, which we did. You need a lot of support also. But support means you need a lot of financial support also in order to achieve these things, and a decent amount of convincing power. Some of the work with the Catholic University of Bolivia had started, but we were not able to engage because this is quite recent, and then all this pandemic started, and things have just stalled for now. So one of the things which you have to do at a particular point is to engage with a lot of people in research. Some of the educational stuff, what I do, so we are trying to do this dual degree, undergraduate and graduate studies. So like one of your supervisors is going to be from Yamagata University, the other one is going to be from St. Fraser or from John Hopkins, or we could add another university. There's going to be a research collaboration, knowledge of transfer, information, and the student gets its equal amount of experience at our university and equal amount of experience at a foreign university. And when the benchmarks are met, the student can actually graduate. So we requested a lot of funding from Japanese government also in order to achieve in order to start these kinds of programs. One which we were involved in running just got over 1 year ago, so we have applied for a new one. So we want to enhance the learning experience. It's not just the learning experience in terms of being at one university and then going to another university. It's not easy on the student as well. But the overall idea is to provide enough of global experience, and the students should learn various working styles. So the Japanese working style is very, very different from American working style. For a student to become a global leader and be sensitive towards different, different ways of working, they need to experience all this. And these have been quite successful. These have been very, very successful programs. Do you have any questions about these kinds of educational programs? No, okay. Now comes the fun part, which is the research part. So like what I do is I do a lot of materials development, and I do a lot of recycling of materials as well. So what kind of materials development I do? I do a lot of hybrid materials, polymers, ceramics, as well as metals. But now there is one particular aspect, is that any materials which we have developed, okay, they should be 3D or 4D printable, or they could be digitally manufactured, okay, or additive manufacturing. All these are almost similar things: 3D, 4D printing, digital fabrication, or additive manufacturing. Of course, then you have to do a lot of characterization and of these materials, uh, to study the material properties, and then their applications are going to be in the following fields: energy storage. They could be energy storage materials. They could be for flexible and stretchable sensors, which we work a lot on, and also soft robotics. So the whole of the idea is to actually develop a sustainable product. Okay. And what is actually a sustainable product? So 15 years ago, I never thought about the environment. But now, after becoming a little bit mature and reading much more, the sustainability aspect and actual product development is going to be, and even now it has started to become a huge thing. So you have to think with like multiple caps on when you are developing. When you say, I want to build, let's say, even an ammonia sensor, but I want this ammonia sensor to be sustainable. So like what it would mean and to have a sustainable ammonia sensor, right? Sounds like stupid, right? But what you have to look at is the materials what you're using, how much harmful they are going to be to the environment. Okay. What are the social and economical implications of actually when you are developing any kind of a product? What is going to be a carbon footprint? People who have visited Taiwan, and you guys might be amazed that every product labeled, right from a cake to a biscuit, actually mentions what is the carbon footprint of this particular product. So to become aware of how much sustainable the processes are is, I believe, is actually quite important if we want our future generations to actually survive. Uh, with this, I would slightly come on to additive manufacturing and sustainable design. Can anybody tell me what do they understand by additive manufacturing? Anybody? That's fine. Doesn't have to be correct. Doesn't have to be a precise definition. Anybody?
Yeah, well, the idea is to take a design and print a three-dimensional embodiment of that design.
Yes. Okay. So there's a slight twist to it. what you're saying is absolutely correct. However, it is defined as a process of joining materials layer by layer. Okay, it's a very precise kind of definition that you to join materials layer by layer from a 3D, to make a 3D object, or from a 3D CAD design. So from a digital to a physical model. So like this is additive manufacturing has been there for a very long time. It's just that it has started to become cheap right now. It's not cheap in the sense, depends on what you want to do. But still, if you are innovative, you can do a lot of um, mm, mm, like a lot of, with cheap instruments you can do a lot of fancy stuff. um, so um, whenever you talk about additive manufacturing, you have to keep 5 things in mind. Okay, first you have to 3D model anything. You to draw a design for your, let's say, sensor or a soft robot, or for whatever, a full battery, a full battery design. Okay, or a full redox flow battery design. um, but this 3D software model, you can do it on AutoCAD, SolidWorks, Tinkercad. There are so many open resource platforms. So it costs you nothing. Then this file has to be converted into an STL file, which is called as a stereolithographic file. Okay, so till now everything is being done on a computer, right? Because your CAD file is going to get converted to a stereolithographic file. This stereolithographic file, you have to convert it into a G code. G code is a machine code. Okay, now you are reaching very close to the physical aspect of like 3D printing. So what does a G code do? G code tells the printer head, okay, to be in what kind of a coordinate at a particular time during printing. And once you click, after the file has been converted to G code, once you click print, your 3D printer or any additive manufacturing machine, okay, is going to print that particular design layer by layer. So this is a very basic overall concept of 3D printing, which most of you might have already known. This is at a very, very fundamental level. However, things become really complex. If you start to use non-standard materials, then your hardware needs to be altered a lot, and that's what I would talk about. So a little bit of background into 3D printing, or like additive manufacturing. The market is worth billions of dollars, roughly around 22 billion or $22 billion by next year or in a couple of years. So there are different types of 3D printings. One is an extrusion based, which means there's an extruder. This is going to be in most of the labs. Everybody went into this thing of 3D printing and people have been buying it. These kinds of 3D printers, the extrusion ones, they cost right from $500 to like $50,000 also, depending on the level of precision you want to achieve, or the number of printer heads you want to have. The next comes direct energy deposition, which means you have a wire of a material and a high energy a power source. It's like kind of welding, but a very fine, precise kind of a welding kind of a process, layer by layer. Then comes then comes solidification of powders. So like this is also called as you can do it by laser sintering. You have a powder bed of fine nanomaterials, but they have to be metallic in nature, or they can be hybrid materials like carbon copper combination kind of things. And a laser goes and strikes, and then and again a layer of powder comes. Again it actually solidifies. Again a layer of powder comes. Again it solidifies. So like this is a really nice process to make a lot of metallic parts, right from automotive to like many other, to even like nozzles for the rockets are also being made using this kind of a process. Then comes photopolymerization, and this is again a very standard kind of a printer. You can a Chinese made photopolymerization printer, you might be able to get it for $500 to $600. The ones which are made, which are by some US companies, $1,000. You want to go much more precise, then it's becomes $2,000. So it's like these are not really expensive. But there is one limitation, and then you have sheet lamination kind of thing where you have a die and then you have a suction, so it would make a 3D laminated object. One of the problems, one of the biggest challenges with all this is actually the lack of materials that are available to print. So we will see how we can overcome such problems. So does anybody knows about Gartner hype cycle? Do you guys have ever encountered it? No? Okay. So so for those who have not encountered encountered Gartner's hype cycle, so like it's a company which does prediction of technology. Okay, so they do it after every 2 years for a particular technology. And also they did for additive manufacturing or like 3D printing. So if you see here, I've been mentioning in between about 4D printing. So 4D printing is not really, like, it has just started. Every technology has 5 stages. One is the innovation trigger. The other is peak of inflated expectations. Then you have then you get this kind of a trough of disillusionment. Then you get slope of enlightenment, and then after that any kind of technology becomes mature. So there have been many technologies which have been in peak of inflated expectations, and when the disillusionment comes, usually here most of the technologies die out. For example, when you guys might have started your PhD, so like carbon nanotubes might have been in their peak, okay? But then what happens is, like, carbon nanotubes did not deliver much, and towards commercialization, then comes a new material such as graphene. So like graphene would be in this peak of inflated expectations right now. In actually 3D printing, the blockchain and 3D printing is actually very new. 3D printing with bonded materials is new. 4D printing is very new. 3D printed variables is new. 3D printed drugs is new. But these things are happening. These are to be a good areas to be in. Okay, but when you look at 3D printed pre-surgery models, they are there right now. Okay, you have 3D printed tooling, jigs, and fixtures. Yes, you can make them. 3D printing for dental devices, yes, it is actually really picking up right now. So materials extrusion kind of technology, it's actually pretty much standard. 3D printing in automotive, it's a lot. It is a lot. The good areas right now, if you want to work in, or if you want to develop the areas, these are the areas which you might want to be in. But there is this risk that some of these areas might die out as well. Whichever way the technology is going, it's always good to actually review such kind of predictions, and they're usually very close to being true. A lot of companies follow it, governments follow it, social researchers as well. What's the next?
Professor,
Yeah.
about
Yes.
the Gardner cycle, does every sector of science have their own curve and their own subjects in
Yes.
the curve?
Yes, they should have one for batteries as well. Okay, if you just want to look at batteries, or if you just want to maybe look at lithium-ion batteries or battery technology, yes, they will have.
Is this statistically based or is
Statistically based? Yeah.
okay?
Yeah. It's not just like somebody is sitting and just thinking and just making without any stats. This is actually backed by a lot of data. Yeah.
Okay.
Any more questions? No. Okay. But do try to find for your own areas as well. It's actually really nice. This is kind of they are summarizing a market report kind of a thing, that this is what is the trend and this is what is going to happen. Okay. So next we will talk about sustainable design. These are, believe me or not, this is something which is, which I don't know how you guys think or how you guys are thinking, but thinking to have a sustainable product, it is going to make a lot of difference. Okay. A lot of difference in the sense you will have a reduced waste. Some of the processes, you will have near zero waste. Okay, sustainable design, you have to think whether you can reuse the product. What is going to be the carbon footprint of the materials what you're acquiring? Our natural, believe me or not, our natural resources are limited. Anybody who thinks that, how many of you work with copper? You use copper as an electrode material anywhere?
We've used copper in electrochemical analysis for application as a drug use.
Okay, so like some of you are using copper, right? I will come on to copper and like some of these materials, and then you would realize that why we should be really careful with actually using these materials. We should be looking out for recycling opportunities. We should think about also kind of environment friendly products. The contamination of water is a huge part. Um, uh, so so the basically we need to find some innovative designs to actually manufacture actually current products. It's a kind of a holistic approach in which you might have some trade-offs. The product what you made might not be 100% as what you expected, but if it is by virtue of some kind of compromises, and you're having less negative impact on actually environment, and you're saving a lot of material. If your product performs 90% as good as the original product, I think that 90% and a material saving, let's say, of 50%, that kind of a product is much more preferable than actually having one which 100% meets your expectations. Of course, when we are talking about human body or human transplants, then there is no compromise. But for most of the products which are which we use every day, I think a little bit of holistic approach needs to be there. And I do believe that materials, new materials development, okay, and combination of machine learning, artificial intelligence, all this has to form an ecosystem, okay, where much more environmentally friendly processes or like designs are made. This follows with United Nations Sustainable Development Goals as well. However, UN has a broader agenda. They, of course, they have a agenda of no poverty, which I don't see how that would be attained. But still, at least in terms of product development, conserving the water, these things can be attained. Where are we standing today? Okay, if you closely look at the slide, this should tell you if anybody was born in 2010, right? What resources and how much resources are left? Um, um, uh, Oil and gas, oil, coal is abundant, right? It is going to be there for next over 100 years. But when you start to come down and look at metals, right? Metals that are also used in renewable energy sources, right? Rechargeable batteries. So like antimony is almost gone. Okay, there is no more antimony left. Uh, uh, it is there only in traces now. When you look at lead, we still have some time, okay, but only 5 years and maximum of 10 years as more with what all traces are left. Indium, okay. Indium has again just 10 years left. Plus you can add 5 more years until 2035 with all the traces. Rare earths, some of them still like till like 2080, but after that they'll be also gone. Zinc by 2025 it's gone, and then only very few traces are left. Silver, the 2028 it's gone. Gold, 2030 it's absolutely gone from actually the surface of Earth. Okay, you will there is no gold left, and gold is a vital component which is used in electronics, which is used, of course, jewelry, and also in crockery. So like gold is one of those precious elements. So from where are you going to get gold? Okay, how are you going to use it when there is no more left? And then copper. Copper are 2035, 2040, it's gone. And so from where are you going to get copper? If we are consuming, if the rate at which we are consuming copper right now, it's actually literally gone from the surface of Earth. This is why sustainability is important. Right now, antimony is going to be as expensive as gold, or even more. Uh, um, we are not getting it. Only traces are left on the Earth's crust. So, what are we going to do, right? Of course, we need to slow down the rate of using these materials, which most of us do not think about, which most of the manufacturers, they do not want to think about, because adopting sustainable operations also requires a lot of investment to begin with. Um, are you convinced that sustainability is important now, or you think that it's? I just wanted to hear from you guys. So, like, what's your take on what should be done?
Well, I think sustainability, it's more of a systemic issue in more ways than one. Like it affects all areas of the economy, business, applications to research, and it's something that, as you mentioned before, is should be holistic.
Mm-hmm.
Yeah.
And so, like, what are we going to do when like copper runs out, right? What are we going to do when indium runs out? So like, we won't be making any more solar panels, or I don't know. So it's quite a complex. I mean, mm, to be very honest, time is running out, right? Say like, to me, I might live until God knows 2050. Okay, if I'm a mean person, I would say that like I don't really care about my future generations, right? Let them die. Okay, as long as I lived happily, that's not my issue. But that actually it should be our issue to have sustainable communities, to have a sustainable life, to have. I mean, it's more how the approach towards product development needs to change. And we have been uh, what we are right now doing is as we guys are trying to develop various different kinds of products which are very simple in design, which already exist, but we are trying to use less of materials, and we are trying to save. um, so in terms of additive manufacturing or 3D printing, so like 3D printing is an ecosystem, okay, which could offer sustainability, efficiency, and actually optimization. So all these things is what additive manufacturing offers. um, there is low, it is low energy intensive. You don't, it consumes less energy. You can have energy savings up to 50 to 70%. You can have so it can reduce the wastage. Up to 90% material savings can take place in actually developing a same product when we are talking about subtractive manufacturing processes. Um, it is really less reduced time to market. You don't need to build up stockpiles. It's like print on demand. There is agility. It's relatively fast. You're not wasting time in like tooling. making various molds for example, for injection molding, and so on. And then this also triggers innovation. If you have a few decent 3D printers on your hand, I can assure you it is going to trigger, whether it's battery research work, whether it's electrode research work, whether it's electrochemical nature, whether you want to make physical sensors, whether you want to make robotics. This gives you a power to design yourself. Otherwise, you have to go and ask a machinist to make some part. That is going to cost like thousands of dollars. Additive manufacturing brings that power back to you. So, and of course, there is no materials wastage. So, like, what are the challenges? Okay, in terms of additive manufacturing. By the way, I keep on mentioning 4D printing. Do you know what is 4D printing? Anybody knows? Anybody has an idea?
Oh, okay, never mind. You can answer, I guess.
Does anybody
4D.
want?
Oh, like 4D printing is where the materials make themselves after being made.
They don't really make. They don't make themselves, but uh, um, uh, these are okay. Um, uh, Stimuli responsive materials. Okay.
Yes.
If you are able to 3D print a stimuli responsive material based on ambient, depends from material to material, based on the ambience around. For example, a change of pH will trigger it to actuate. Okay. A high saline content will actually make a material to morph into a different shape. And these shapes are pre-programmed into the material. Okay. As soon as a high salt water content comes, it changes its shape. Um, uh, or the temperature changes, it actually morphs into a different shape. Um, uh, of course, variation of pH is also a very good example. So based on the ambient conditions, the material is able to change its shape with time. It can be fast, or it can be soft, or it can be slow. So like it is essentially 3D printing of shape responsive materials, okay, which morph with time. It could be shape memory polymers, shape memory gels. It could be 3D printing of shape memory alloys, alloys, shape memory metals, or alloys are much faster in response as compared to shape memory polymers. But still, both of them have their own place. So shape memory polymers are used in one of the categories of soft robotics, okay, that they would morph automatically with change in the ambient conditions. Okay, so let's get back to the, do you have any questions on this? 4D printing?
Yes, when you talk about it morphing into different shapes, can you talk about how you control how it morphs into the shapes you want, and how do you control or get it to do what you want?
Okay, so we have to synthesize different materials. For example, you can synthesize is a water absorbing material. Essentially, you can synthesize a hydrogel, okay, and you can print it in such a shape that during its temperature responsive hydrogel, okay, that when the temperature of water would change, okay, uh, um, uh, let's say you want a material to grab hold when the temperature changes, right? Let's say I want to actually grab hold this bottle with a soft robot or a material which is 3D printed, and it changes with changes with temperature. So what I'm going to do is I might print a bilayer structure. Okay, two materials which expand and contract with uh, uh, expand or at different temperatures. So one material is expanding faster than the other for an actuation to actually take place. So if the material has a shape memory, it would, when the temperature comes back to cold, okay, let's say 10 degrees, and you can really specify these temperatures. You can make a very temperature specific hydrogels that they would expand or contract at a particular temperature. So now you have a bilayer. One is expanding at one particular rate, and the other is going to expand at a different rate. So you can make it bend. You can make your hydrogels bend with a gradual increase in temperature. So these kinds of things form a gripper that I would show you I think I should have a picture of of some of these like grippers. So a bilayer structure with a variable expansion rate would actually form a gripper, which would grip. Does that kind of clarify something, or it has made it more confusing?
Oh, that helps. Thanks. That's very interesting. Appreciate it.
Uh, um, uh, so essentially these hydrogels we have to synthesize and by varying the La and Sa values, we could actually make them expand and contract at different temperatures. So okay, some of the challenges in actually 3D and 4D printing.
Professor, can I interrupt?
Yeah.
Yes, sir. So I want to just I want to follow up on the question that was just asked. Is it software predicted whether a material will morph into a designated shape, or is it is it really calculations that we have to manually execute?
See, a, a shape memory material which has been synthesized to morph at a particular temperature. Okay, that is that is a combination of the materials what you're using. Okay, but once let's say you have um, printed a kind of a flower kind of a structure, right, with like various cantilevers. Okay, that is digitally controlled by your software, and that is going to become its like um, original shape. Okay, when the temperature would change, it would start to bend. Okay, and it would grab a thing. Then again the temperature when it changes, it would come back to temperature. When it becomes cold, it would come back to its original shape, which is the shape in which it was printed. So you can do a cycling, right? Hold release. So I can grab lift up a bottle, okay, and actually change the temperature and actually release it again. So this process can be repeated again and again and again.
Great.
Okay. So like some of the not some one of the biggest challenges in actually 3D 4D printing is actually lack of materials. We don't have enough of materials which we can print, especially to make really reliable batteries, or like redox flow batteries, or like sensors. It's very difficult to 3D print hybrid materials. In this slide, you would be able to see that what we have done is we have tried to design our own 3D printers. We have developed our own 3D printers, which actually takes just bulk materials. They don't take filaments. They take bulk materials. By bulk, I mean here like they will take grains of materials, okay, powders or grains of materials, and we can actually pretty much 3D print hard and soft materials together. We can print conductors and insulators together, and we can come down to a feature size of almost 100 micrometers. 100 micron precision printing can be also done. One of the micro grid-like structures, bottom left figures actually shows that we can do very precise micro 3D printing as well. But it's challenging. It's not like, you just simply develop a nozzle. There is a lot of how much pressure a nozzle could handle. You make a 50 micron nozzle through which a fluid has to pass. You need a lot of pressure to be applied. So we made this screw-based extruder system by which we can essentially achieve down to 100 micron feature sizes. Any questions?
Yeah, so at the bottom there, it says developing a 150 micrometer nozzles. What are there any specific applications that those size nozzles would deliver for certain manufacturing applications?
Oh yeah, many. A lot of one is you could make things like accelerometers simply using additive manufacturing. You could make gyroscopes. These are some of those simplest examples. You can make filter membranes. This microgrid shows you freestanding grid kind of or a fence kind of a structure, repeated one after the other, one after the other. You could use for capturing various cells, right? You can make cell traps out of it. Otherwise, you have to use photolithography for it. Here, it's just a simple machine. Photolithography wastes a lot of materials. This is like zero wastage, and you are just building layer by layer. You could use a similar carbon-based material, and then you could make these microstructured electrodes, carbon-based electrodes, for your batteries or for various other applications. You could make electrodes for metal layer batteries. So the applications go as far as your imagination can go to. Smaller the structure, the smaller the feature size you print, the process becomes much more expensive. But it also gives you in the world to explore in terms of micro, nano, like regimes. Nano 3D printing is also possible, but it's ridiculously expensive and ridiculously slow. That's why it has not caught up as yet. So, any more questions?
Yes, I'll follow up on the question. It's nice because in a previous project we were working with nanopores, and we were trying to get the signal from molecules passing through the pores, and it's not so straightforward to make these structures. But this photo here is quite impressive, because if it can be achieved by simple printing, this would be very cost effective, whereas it would avoid complex technical instruments such as focused ion beams or lithography, as you mentioned. My question now is what is like the price comparison, the cost comparison of a focused ion beam machine, or and compared to like a 3D printer? Is it considerably different?
Oh yeah. This was like I mean, heaven and hell, right? That that level of difference, extreme. These are two extreme poles, right? A lot of these, a lot of these equipments, if you are a little bit techy, you can actually do them. You can actually make them yourself as well. So, so, so like a lot of these we are making in our own lab ourselves, right? So like graduate students are the cheapest labor which you can skilled labor which you can have. So like these can be done very easily. So yes, reaching to extreme like 100 nanometers, I don't know if that can be done using cheap methods. Otherwise it's like relatively cheap. I mean, you can buy a 3D printer for $10,000 with a spot size of 5 micron. Okay, 5 micrometer. So that is really impressive. With a spot size of 5 micron, it's actually very impressive for like $10,000. So, and fib, 1.5 million, right? A million, yeah. So there's a big. It's not like 200K. Fib is not 200K because it's fib and SEM together, right?
Yes.
So it's yeah, you're a really good one, like 2 million. So.
But this is very impressive, Professor.
Yeah, it's you can so the I have entered. My intention was never. I have accidentally entered into this area. There's a different story behind it how I entered into this area, but yeah, let's go. So you can see here is a video. So this is an elastomer. Some of you might have used polydimethyl siloxane, PDMS, right? So if you have used it, this is a thermoplastic version of PDMS. So this is showing how the hopper takes in the material, okay, and it eventually prints it. So this is a single screw version. We are working on a second version, which is a twin screw version, which gives much more smoother surfaces after being printed. So like here, okay, interesting. Here you can see what all we have 3D printed using the printer. What you saw there was costed us one, two, two like students, which were free. We didn't have to pay much, and probably $2,000. That's it. So what we have been able to print using it are various things. Some metallic gears we can print right from metals. Okay. A lot of carbon-based conductive ionic gel materials. This we had published in Nature Polymer. Soft conductive nanocomposite based on ionic liquid carbon nanotube for 3D printable flexible electronics. These are the images of that. We can power up circuits. It's quite flexible. This has come out from a very, very expensive system which we have been designing and working on in-house. So this we have submitted to Nature Communications. We are waiting for its whatever review. So this is like 3D printed gallium doped zinc oxide flexible UV detectors. So all these things are actually possible by actually additive manufacturing. It's just that we need to keep on developing materials after materials, or we need to keep on modifying materials after materials. So that modification process is not very straightforward to us. So it is a learning curve through which we have to go to have more materials for additive manufacturing. Otherwise, 3D printing would remain just stuck to building just like toys and gadgets and small things at home or for enthusiasts unless the materials diversify. So do you have any questions on this? No? Okay. So here also some more images. These are quite impressive. So these are drug reservoirs, microcapsules to swallow with drug in them. These have been 3D printed. These have been printed on actually polyamide. We have these flexible, stretchable, variable sensors. Okay, again using CNT and ionic gels for your ECG measurements. These are again sensors. Some of the printing. This is 2D printing. This is done on a fabric. This was meant to filter out some cells. And I don't know what has happened to this project recently. But this we have published recently on 3D printed reservoirs for drug delivery. Okay. So like essentially one of the biggest ideas is we want to have micro optics, micro sensors, microfluidics, all of these things. We want to build one actually device which performs multiple functions by employing 3D printing. We have not reached there as yet. We want to have this micro nano fabricated structures and like devices which are 3D printable. So this is a long-term project. This is the bigger vision and goal where we want to head towards. So, some more structures. Here it might start to become a little bit interesting. This is a MIM material. This is actually your metal injection molding material, which we had tried to 3D print. This is stainless steel. So this is stainless steel after printing. A is after printing and B is after sintering it, sintering at a high temperature. And we get actually stainless steel in the end. The C figure is actually elastomer material. Elastomers are very difficult to 3D print. And then there is a wood composite, which is the D, which is shown. So we are able to print these like various kinds of soft, hard, steel, and also recently copper we are 3D printing. So here are some other 3D printable examples. Such structures out of elastomers or shape memory gels are really difficult to print. So this we recently published in Soft Matter 1.5 years ago. So these are shape memory materials, and what we have printed. So like this is a finger model. So we want this finger to move eventually. That's a long-term goal. To 3D print a single structure of a cylinder is also very difficult. It is just these structures have been printed just to show that we can 3D print them, because it is a big challenge to do so. Are you able to see in figure C some lines, gratings kinds of, so these gratings are there because of 3D printing. It leaves a mark, layer after layer. So do you have any questions regarding this?
Professor, the cylinder, does it also have those gratings, the lines?
Yes, it will also have, yeah. It's just that the angle and the light angle might be, all of them will have. So next comes, what else are we trying to do? We are trying to print again a lot of inks, materials, to make various kinds of traces as a low-cost fabrication processes on substrates like papers, elastomers. We want to 3D print them. So like this is again one of those papers which we had published recently, that we are 3D printing on a photographic paper, and we are trying to study the properties of the ink, the adhesion between the paper substrate and the inks, and what is the effect of sintering, or like or the temperature of sintering, the cycles of sintering, what kind of cracks appear, or so we've done an in-depth study of it, and try to optimize processes, that if we can print something on a very extremely low cost substrate, we can print even like things like vapor chromic materials to sense ammonia. So the whole of the idea is first to investigate that the sensor what we are building, is it going to withstand? Of course, we know that the sensor would work, the material would work, but will it withstand the real world scenario or not? For example, paper-based sensors have a big challenge. In case where there is where the humidity rises, do paper-based sensors really work properly, or there is a lot of drift in the data? So a lot of these things also need to be investigated. One thing which I seriously do not like about a lot of people who work in sensors is they will take a material, they will test for its sensing properties, but very few check in case of gas sensors, especially what is going to be the effect of humidity. So humidity is a big killer, right? A lot of people don't do it. And I simply reject the paper based on that, because you have not done humidity testing. Yes, the initial results tell you that material is good, but if it's not going to be applicable in a real world scenario, just because a material which you develop can sense doesn't mean that it is going to be one of those best materials. So like further work needs to be done. Moving from here, we move to a high temperature material, which is called as an armored paper. So the armored paper, it can withstand temperatures up to 350 to 400 degrees. It's made by the same company, which I earlier mentioned, Teijin. So like Teijin makes it. It's a high temperature paper. We have been trying to study its adhesive properties, its like porosity, and the drift of signals of the currents, what you get at like various temperatures. Up till 100, up till 350 degrees, the paper does not burns out or does not shows any kind of degradation. Crossing 400, it does. So this is one of the work which we are trying to pursue right now for high temperature sensors. So in terms of these like paper-based stuff, so high temperature paper-based sensors and electronics is of interest. Shape memory-based paper is of interest, especially when we're talking about sustainability. Cellulose-based tough biomaterials are of interest, like 3D printable cellulose biomaterials for tissue engineering. The way I see our lab doing is, we can make these things for you. If you want to do tissue engineering, we can do that. We can make these materials for you, to do tissue engineering. Okay. So like things like these. So like things like self-healing paper, which is again a kind of a shape memory effect. And then cellulose-based nanocomposites for like soft robotics, trying to go much more towards a greener side, towards more sustainable side, recoverable materials, so that you can, after using, this could be recycled, minimum carbon footprint, and so on. So how are we doing for time? Is it okay? The time
We are
part?
almost out of the time, so
Okay.
I mean, you can.
What I would show you is, what we have done is, we have recently made a fully integrated vanadium redox flow battery, um, mm, which is 3D, which is fully 3D printable except the membrane, because the membrane is of Nafion. We did not use it. Otherwise, it's like fully 3D printable vanadium redox flow battery. Right from only the screws were like metal. Otherwise, the whole of the system, even screws, we could have 3D printed. But right from the end plate, your spacer, current collector, electrode, okay, all these frames, including current collector, which has micro channels in it, all this was actually 3D printed, and various designs were made until we reached an optimum design. You can see this cell operating. We can light up a fan. It works like pretty nice. So, this is another kind of version of it. With a much more cleaner background. Okay. So like, what is our ongoing work? We'll do a lot of paper-based stuff for flexible sensors and electronics, of course, 3D printable on the substrates. We're going to collaborate with people from machine learning and artificial intelligence So there needs to be collaboration among AI, machine learning, and folks from material science. We're going to collaborate with some people who are more into AI and batteries, things like these. We're going to optimize more of 3D, 4D printing parameters. We are developing a twin screw kind of extrusion system. So like 4D printable shape-shifting materials are obviously all are of great interest to soft robotics. Currently, we are just doing hydrogels, but we want to move on to like even like metal based. We're going to furthermore optimize micro nano structures on our electrodes and micro nano channels. And of course, from currently we do a 5 micron resolution. That 3D printer which has been developed is going to be launched in market pretty soon. So our university innovation office is, along with a few companies, Mitsubishi Chemicals, they are going to be putting it into market. By the end of the day, I think people from material science, additive manufacturing, big data, machine learning, AI, all of us need to, work together and fully utilize and balance the production consumption of energy to maximize the efficiency for sustainable systems, because we do want a sustainable society. As you have seen that copper is going to run out in the next 10 years, antimony is gone, so we need to develop these sustainable processes. Some of the agencies from which money comes from, a lot of industry, of course, I do take a lot of interns from actually Canada through my test program. But when I was in Canada, I utilized a lot of NSERC and SRED programs. In Japan, there's JSPS, GST. Seiki is the company with which we have developed the printer. Nippon Graphite Fiber Corporation, and Neo Materials. They do a lot of rare earth magnetics. So all these are like sponsors, and of course the granting agencies. And if you have any questions, please. I've skipped a big part of recycling of vanadium, but I will send you the presentation, and so you can have it and circulate.
Thank you.
So questions?
Yes, Professor, I have 2 questions. May I go ahead?
Yeah, please.
The video with the fuel cell animating the fan, that was really astounding. What is the chemical reaction occurring in the fuel cell? Is it the water splitting?
No. It's like it's a vanadium redox flow battery, right? V3, V5.
Okay. So these the points of entry of the fluid inside the fuel cell. Okay, yes, okay. Okay, that's nice. Thank you, Professor. And the second question, could I see again the organizations that were affiliated with your work, please? Yes.
Yeah. You will have this. I can send you the PowerPoint.
Yes.
So this, from my side, anything is open. If anybody wants to come for an internship for a while, you can talk with your mentors, or if some professors are here, I would really encourage, if there is a common ground found in terms of research, I am more than happy to welcome any of the interns from actually Clarkson. We do have a program through which we can, this is to come through your supervisors or like professors, and just you cannot ask me you can ask me directly, but this will not happen without permission of your supervisors. Right now, anyways, this COVID-19 is going on. Mm, but during normal times, we do have a program by which we guys have some kind of funds through which we can bring in an intern for a few months, typically 3 months, and we pay for their air ticket and their accommodation, and a very small stipend, right? So it's like your air ticket plus $1,000 for you guys to live. Your accommodation, you will be surprised, is actually subsidized to $150, or like maximum, if you use a lot of electricity and water, will be $200 per month. Okay, per month. That's what you need to pay. So essentially, rest $800 are for you to spend your food and so on. So we do have a program, but this has to come through one of your professors, and then we can kind of host you if you want to have that experience. So
hello, Prof.
Yes.
Can you hear me, please? Hello?
Yes, I can hear you.
Oh, great. Thank you for the talk. It was quite interesting. I think my area of interest in the talk is the sensor area and the interest I'm building in batteries. I've recently concluded a study in electrochemical sensors where I published a paper in ECS journals. And at the moment, I'm an independent researcher, and I'm actually interested in seeing if I can learn further on the application of my sensor, high temperature electrochemical sensors for sensing magnesium in non-ferrous alloys. And I don't know if there's opportunity for a postdoc, and also if I can apply my solid electrolytes in developing batteries, magnesium batteries.
Sure. For like things like postdoc, the best thing to have is a GSPS fellowship. We need to apply for that. That is by far the most lucrative and the most money. Like, your salary is going to be pretty good. So yes, if you want to apply, let me know. Send me your CV, and we can look into it and like move ahead. And in terms of applying your electrolyte, why not? We can explore into we can explore the options.
Okay, that's nice. I'll email you my CV.
Sure.
All right, thanks.
Professor, I think some of our participants are leaving, so I just want to have a just interruption, having a group picture, and then you can continue questions like everybody. And if you would like to turn on your video, like camera, so everybody, you can do it, and Ben, you can take care of the.
Oh, okay. Yeah, sorry. I was trying to figure out how to do it, but I guess it's just that you had to stop sharing for everybody to be viewed. Thank you very much. So let's see. All right, everybody smile.
Yeah.
All right, and it should be good. Thank you very much.
Thank you. So go ahead, and everybody, if you have.
Like, if you have questions, please.
Professor,
Yes.
On a more personal level, how good is your Japanese?
Reasonably okay. I can get around. It goes as far as that. Yeah.
How long did it take you to be comfortable in communicating in Japanese?
At least a couple of years.
Wow. Okay.
I was not motivated as well. So if you're motivated, you can pick it up quickly.
Thank you, Professor.
My usually task is just to do. I interact in very basic Japanese with like students. So you need to understand Japanese has various levels, right? The way it's the way you interact with your senior is different from way you might interact with your equal or junior. So students have to address to me in a very different kind of a Japanese when they would talk to me. Okay, so to learn these finer things about language, it's not easy. At least for me, it's not easy. So it takes time. At least it took time for me, but I know people who have done it pretty fast.
You had also mentioned the difference between the work style of a Japanese versus a North American student. Could you talk a little bit about how you found that to be when you arrived in Japan?
How I found it to be. So I would be interacting in a similar way with students the way I used to do it in actually North America, but here students are very formal most of the time. The only informal part is when you go for drinking. Okay, that is the time when they are, I won't say allowed to open up, but this is kind of a thing that then they open up. So you get drunk, students open up. Okay, so but still, because you are the mentor, you are the professor, you still try to maintain a little bit of distance. But at the time, even if they use some bad words, it's okay. So you embrace them as they are. And next morning when you go to your office, that wall is again there. Okay, the big barrier wall is actually again there. So it's also society wise. Uh, Different societies work in a different way. So here there is a big culture of nomakais. Nomakai means going to an izukaya for drinking, a party essentially. So if a new intern student comes, so there is going to be a nomakai, right? If a new professor comes, so students will have a nomakai, professors will have a nomakai, and then there'll be a joint one, students and professors. Just for one person, you have three parties going on, right? So, so it's a different culture. So like then you start to observe how these, at what point do the walls break down. Uh, hmm, it's much more visible in Japan as compared to, because during everyday life it's very formal. I mean, not very formal in the sense that they're going to be bowing down in front of me every time they see me. But during a formal interaction, they will bow down to me, and I would also. My bow will be at a less slant than theirs. If I go and meet a dean, so I I have to bow down at a much more angle than him. So it's a kind of that hierarchical system, right? Uh, so you don't show your back, okay, to your, I just cannot go once, turn around and walk, right? I have to walk backwards if I'm going to meet my university president, right? Mm. Some things are nice, cool, the way I used to see it in movies. So I experienced those. So it was a good experience. Yeah. I mean, I don't mind it that it's like. I in fact enjoy it. I said, like, look, this is what I used to see in movies, and I'm in it right now. So
Awesome. That's very interesting. Thank you very much.
yeah.
All right. Any questions? We are just getting to 11, and I think some of us having meetings. So if anyone have a questions, go ahead. And if you want to continue, I'm gonna leave, but you can stay and.
Yeah.
All right.
I had a question.
Yeah.
In terms of sustainability, would you recommend using life cycle analysis in terms of projects?
Yes. Yes, of course, definitely. Uh, I have not gone into, see the topic what I had chosen. I did not want to really go heavily into a lot of numbers right now, because I actually honestly don't know what I was also expecting. But next time if we meet again, we would talk about really like big numbers involved in this, a lot of stats. Um, you know, um, uh, to be very honest, all the technological developments what we have done, they have been amazing, right? Uh, Plastic has been amazing, but we have not looked into the facts right now that, um, for example, most of your window frames these days are made out of PVC, okay, which is a plastic. So which has a life cycle of 15 to 20 years, okay. Um, and it is a big carbon footprint. It is not degradable. However, if you use wood, right, wood could be potentially locally sourced. Wood has a life cycle of like 60 years, 70 years as a wooden frame, and technically a wooden frame should not cost more. Um, uh, uh, so the price breakdown comes to the similar. I mean, a wooden frame versus a PVC frame comes at a same cost, but people are still preferring these days PVC frames, because of um, it looks sleek. Wood needs care, a little bit of care, right? PVC does not need care. You might need to paint your wood after a few years, okay, because of the weathering. So you have a wooden frame, snowfall, light, wind, so the paint would start to chip off. So you have to repaint it. It requires a little bit of care, and we guys are lazy enough that we don't want to take care. We want it to be already taken care of. But in terms of what is going to happen if we keep on amassing so much amount of non-biodegradable materials, right? Um, the life cycle of wood is more, in terms of. So we have to think, what do we want in our lives? I mean, look at in this pandemic, it has brought the Homo sapiens, which is our species, to its knees, right? Are we capable to fight against all these things? Um, hmm, so um, uh, uh, I've been reading so many wildlife forms they are now actually showing out because there is less noise pollution. There is turtles are hatching out of eggs even during daytime because there is no noise, nobody's thumping on them. So the turtle population is increasing. So we need to little bit think about how we develop our societies, which become eventually sustainable. And it is a whole approach. It's not just developing a product. It's as simple as having a wooden frame instead of a PVC frame. It's just a matter of choice, right? So yes, I would definitely always, of course, the life cycle, for example, of some, in some cases, if you have a material whose life cycle is like, which doesn't degrades, maybe 500 years, okay, versus let's say wood, which would last for 10 years. So okay, that 500 year thing, small amount of them, it's okay to have, right? We could have it. But now saying that, okay, I'm going to use the same material to build everything, and come on, man, it is going to destroy everything, right? So there's sometimes biodegradability is also a very, very important aspect. When honestly I was of your age, I really didn't care. I never thought about it even. I think the younger generation is much more aware about sustainability, more of holistic approaches. They are advocates towards it. When I was young, to us it was like one of the last thoughts in our mind. So I'm really happy with the upcoming future scientists, engineers who are thinking strongly this way.
Thank you.
Yeah. Any more? Anybody has any more questions?
Any more questions?
All right, so it's roughly 11 then. I think this is probably a good time to conclude.
Sure.
Thank you so much again, Professor Khosla. This is a great talk.
Yeah,
And yeah, it was very nice to see all the other clubs and chapters join together today. And we hope to see you all again soon at any other events.
Yep.
Thank you very much, Professor Khosla, for your effort, and thank you for your time. It's close to 12 a.m., I guess, in Japan.
Yes, it's like midnight. Yeah.
Wow.
Hopefully, we'll meet in Hawaii meeting if we get to.
Sure.
Yeah.
Do please let me know if any one of you needs any help. Okay.
Sure.
Sorry. On my part, I think because of time difference, I'm somewhere in Africa at the moment.
Okay.
I missed the early part of the lecture. Is it possible to get the slide?
Yes, sure.
Yes.
Additionally, a recording will be put on YouTube under the Clarkson ECS channel if you'd like.
Oh, great. That's good.
Online. Thank you, everyone. Thank you, Professor.
All right.
Have a good day.
Yeah, thank you, Prof.
Thank you.
You too.